Can everyone hear me? Okay, thanks, George. Okay, well, welcome everyone. Let's go ahead and get started. It looks like it's 2 o'clock. I will say a prayer and then we're going to start on radiation. Our Father in heaven, we're grateful that we can pray as we begin this class today. Please bless us that we can understand one another even across these long distances. Bless those who are sick and that they may get better. We pray that this virus will be slowed. We pray that we can go back to normal soon, that we can be prepared to fast on Friday. We're grateful for the opportunity we still have to learn, even amid this time. Bless the students, especially as they are getting towards the end of the semester, that they can manage their time and be prepared for finals. Bless us now that we can learn about this new topic of radiation, and we say these things in the name of Jesus Christ, amen. Okay, so it's kind of an exciting time. We have 3 days of new material. We actually have 2 lectures, lectures 33 and 34. They're spread over 3 days to kind of slow down a little bit. So this class is, we have today, Wednesday, Friday, and Monday. We're going to spend on 2 lectures, 33, 34 for radiation. You have 2 homeworks left over these 3 days. And one will be due Monday, and it's due at 5 o'clock to give you a little extra time to talk to the TA if you need to. And then one will be due Wednesday. And then that is it. I don't know if you can believe it, but you're actually going to survive heat and mass transfer. You're almost done with this junior year. I know it seems like a crazy time, and you probably had it harder than almost any other class so far because of this crazy virus stuff. So congratulations. Radiation is actually, I think, kind of a fun topic. It can get very complex, but we're not going to ever get into the super complexities of this. We're going to focus mostly on the basics, because in engineering calculations, that gets us pretty far, especially unless you are building something for outer space. So if you go work for NASA, then you might need to review a little more radiation, because radiation is the only way heat transfer occurs in space, or if you're dealing with some sort of specialized type things. But most of the time, what we deal with, we're mostly kind of doing simple energy balances where we might have radiation, and we'll show you some examples of that. So let's go through some basics of radiation first of all. You recall, I don't know if you recall this, but in PChem, you probably should have learned about the electromagnetic spectrum. You probably learned about it in high school or junior high or elementary. Anything that is above 0 Kelvin will emit radiation. And radiation has a dual nature. It has waves. It behaves sometimes like waves and sometimes behaves like particles. That's the best way we know how to describe it. And that seems ambiguous, but we know that it's wave-like because we can interfere with it. We can use some experiments like slit experiments and things like that to change in interference to change the patterns. But we also know that it's particle-like because we can see the effects of these photons, these quanta of energy. That is kind of all the PChem review you really need to know, other than remember that because of this dual nature, there's these fundamental relationships where I can get the energy of a electromagnetic wave based on its wavelength or its frequency and Planck's constant. And Planck's constant is also, or it's also related to the speed of light, and the frequency and the wavelength are related through the speed of light constant. And so these are just basically kind of conversions, right? You go between frequency and wavelength. You've probably seen some sort of figures like this. I'm actually pretty proud of this figure. I made it myself. I have to make my own, right? Because I don't want copyright issues. But as you increase in wavelength, then the energy goes down. And that's why energy is going this way. So X-rays, gamma rays, are very small. They have a lot of energy. FM radio waves, things like that, have very long wavelengths and have less frequency. So radio waves are kind of the limit of what we do practically, and they're very long. You can see that we're talking like kilometer size waves in certain cases. When we are emitting it, most things at normal temperatures emit wavelengths in the UV, visible, and infrared spectra. For example, the sun, as you know, it emits visible light. That's why we can see. It also emits UV light. That's why we get sunburned. It also emits infrared, which we don't see, but it's outside our visible range. And you can see the visible spectrum is very small across the wavelength compared to what we see what we see of the other types of waves. So the first thing you want to remember from this part of the lecture is that everything that is above 0 Kelvin emits electromagnetic radiation, and it's going to be in the near UV or near infrared and visible type spectrum. Also remember that wavelength and frequency are interrelated through the speed of light, and that you can get the energy of a wave through those fundamental equations that you see there relating Planck's constant to the energy and the frequency, or the energy and the wavelength. So any questions about that so far? You've probably seen that sort of thing before. Okay. So whenever you have radiation hitting something, that's usually what we care about. We want to know how something's going to heat up or cool down relative because of convection that we've already talked about, but also because of radiation if it's important. So we've got to start figuring out how to describe radiation. When you have a source that's emitting radiation, hitting some sort of other object, this rectangle, there's a few things that can happen. So irradiation is the term we're going to use for the incoming radiation, the thing on the object. When that irradiation hits something, and we usually give it something called G, without any, a symbol called G without any, say, subscripts or something like that. There's three things that can happen to that radiation. It can be absorbed into it. It can be reflected, like with a mirror, or it can be transmitted through it, like glass. And every object has properties associated with it that tell us what fraction of the irradiation will be reflected and will be absorbed and will be transmitted. And these are things you have to measure. You'll also notice that I have something here that says, this is not a negative sign, it's like a dash or whatever. Let's put bullets right here. The amount or the fraction of the irradiation that is absorbed is what we call the absorptivity. And that's something we have to measure. The amount of reflection, the amount of the irradiation that's reflected is called the reflectivity of that material, and the amount that is transmitted is called the transmissivity of that material. And the alpha and the rho and the tau all add up to 1, because there's only 3 things that can happen with that incoming radiation. It can either be absorbed, it can be reflected, or it can go through and be transmitted through. So class has a very high transmission. So, you know, like 0.99. Very little of it is absorbing or reflecting. Something like a mirror has a very high reflectivity. Very little of it is being absorbed or transmitted. And again, these are things you'd have to look up in a table or a book or something like that. Our book has some values for this. And so just to remind you that those 3 properties have to sum up to 1, and it's something you have to look up. Now, there's one other thing that's going to happen with this body, this object that things are hitting. Because it's above 0 Kelvin, it's also going to emit some radiation. It's going to have emission. And that emission is what we have to describe now. The reflectivity, the absorption, the transmission, that's something you just kind of look up in a book, and you can account for it pretty easily in your energy balance. It's just a constant times what's ever coming in. But the emission is something we've got to learn how to describe. Now, you've probably seen these kind of Stefan Boltzmann's law before. That's how we're eventually going to describe it, but where does this come from? That's what we're going to go through here for a minute. You can see just kind of some definitions. For opaque objects, that means there's no transmission. For a black body, and we'll talk more about black bodies in a second, that means there's no transmission and there's no reflection. Everything gets absorbed. Just kind of some definitions. I think I missed one up here too. Oh no, I got all that. And so, any questions up to this point? I didn't check the chats. I kind of see that popping in and popping out. It's probably you guys just talking about Hogwarts, right?
I have a question.
Yeah.
What would be an example of an opaque object?
So, like your house wall is an opaque object. When light hits it, nothing goes through it. Now, maybe your blinds on your, if you don't have blackout blinds on your rooms in your house, then part of that light still gets through. But anything that light doesn't get through. So if I go into a dark room, anything in the Clyde building, so to speak, in the middle of the Clyde building, if I turn all the lights on, there's no light. Those are opaque walls. There's no external light getting through those. Does that make sense?
Yeah, thanks.
Any other questions?
So opaque objects are not black bodies.
They don't have to be black bodies. No, they can be, but they're not necessarily black bodies. If they are black bodies, then they also don't reflect anything. So you have to be an opaque object to be a black body, but not the other way around.
So black body would be a subset of opaque then?
Yes.
Okay.
In the reading, it said that snow could be modeled as a black body. Is there another example of black body? And then like
yes, we'll talk about black body just here in a second as we go down this. It's a very important limiting case. The sun acts like a black body because it's so big and so diffuse. If you have an object, a small object in a really big room, the radiation coming from that really big room looks black, the object looks black body because of that. And the book kind of goes through all the technical proofs of that. I think they're kind of boring to go through, and I just accept them. If you don't accept them, you can go through the book. But those are kind of some ideas of black bodies. Small objects in really big rooms or big surroundings or something like that. The sun behaves like a black body, and then we can also make things that look very black body, where they don't reflect anything and they don't transmit anything.
That makes sense. Thank you.
Anything else? I want to go kind of slow through here to make sure everyone's kind of caught up. I know this is new to everyone, but it comes out that it won't be too hard to describe once we get down to it. One more thing before we go into section 3 right here. The radiosity is defined as everything that's reflected plus everything that's emitted. It's basically everything coming off the object. If I go back to my diagram right here, notice there's only 2 lines that are going off the object. It's the reflection and the emission. And so this will become more important for lecture 34. And we'll probably start lecture 34 next time and finish it up Monday. So just kind of know that's a definition, and I'll return to that later.
Dr. Knotts,
So, yeah.
Does the emission take into account the transmission?
No, transmission just appears as if nothing happened. That fraction of the emission, or that fraction of the irradiation, the light, the wave, just doesn't even affect it. It doesn't get absorbed. It doesn't reflect off, and it doesn't heat the object up, because it just passes through.
Okay.
Does that make sense?
Yeah.
So it would not be part of the emission because nothing heated it up. It doesn't heat up. So why is radiation complex? If you did the reading, or tried to do the reading, because right, it's kind of a complex thing I told you to do, skip these parts, do all that sort of thing. There's all sorts of math in there, all sorts of double integrals. So I'm never gonna have you do those double integrals in the sense that on a test or a quiz or anything like that, but I want you to understand why they're there. And then if you ever needed to go back and be more exact, you could do that. But the reason it's complex is because when something emits, it's direction dependent, and all of the properties, the emissivity, the absorptivity, the reflectivity, they can also be direction dependent. And that's why it gets complex. The other reason is it also depends on the wavelength of light. For example, the reflectivity of almost anything on our bodies except bone is very small to X-rays, right? X-rays go through almost everything but bone. And then when they hit the bone, then they don't go through. And that's why you can get these X-rays of your bones. And so you have to, with whatever you're worried about, you got to make sure you're taking into account any irradiation that's coming into the object, that epsilon and sigma and rho, and not sigma, epsilon, rho, tau, and alpha can all be direction dependent and lambda dependent. And so everything has to now become a double integral. Let's kind of demonstrate that out. Let's say you have this really small object sitting here. I can draw a hemisphere around this object to determine all of the emission out of this. And this thing, if it's above 0 Kelvin, is going to be emitting radiation in all directions. And it's going to emit lots of different lambdas. And you have to take into account every lambda. And so the way we do this mathematically is we say we have an I, say lambda equals 530 nanometers. And then we have an I that is lambda equal 540 nanometers, all the way across all the region that's emitting, all the wavelengths that are emitting. So to get the total emissive power, the total emission that's coming out of here, we first have to do an integral over this area. And that's what you see here for every lambda. So there's lots of different lambdas. And I have an epsilon for each one of those. Then I've got to take all those and integrate each one of those across every lambda. to get the total emissive power. So it's a double integral, 1 over lambda, 1 over area, or direction. And this part, this I lambda, can get very complex as it integrates over the direction, because I might be emitting really well in one direction because of crystal structure or something like that, compared to another direction. So it can get very complex. So it's not only complex because of the double integrals, it's complex because at every angle or theta, things can change. Now, we're always going to assume some things that make that easier later, but that's in general what you have to do. The second part of the complexity is I have to do the same thing to take into account anything that is coming into this object from the outside. I don't have a diagram on that, so I just kind of drew it right there. If I'm trying to calculate how much irradiation there is, I have to figure out all of this stuff that's coming in at every wavelength. And then I have to integrate over all the area, because it can change if it's coming in like this, like this, like this, similar to what we talked about with the sun. The sun in the evening doesn't feel as hot because the waves are kind of glancing off us, versus when it's right overhead, they're hitting us directly. That's all into this area integral. It's the direction part. And then we have to integrate over all the lambdas, because I might absorb something at one lambda and not absorb things at another lambda. And so there's a double integral to figure out all the emission. There's a double integral to figure out everything that's coming in. And then you have to sum all that up. And then finally, you've got to take into account how much is reflected. And so everything that's going out is not just part of emission, it's also part of reflection. And that's also a double integral. So again, I'm not going to have you go through all these double integrals. I just want you to see why they're there. They're there because everything is lambda dependent and everything is direction dependent. So questions about that? Okay.
Dr. Knotts,
Yeah.
how do you know which eye to use? Like if you run like a Python code, would you just have an array or like a lens space of all these different possible types of wavelengths, or do we measure them before?
So we will talk about that. And yes, we know Planck, one of the things that he figured out, we'll see here in a second with black body, is he figured out at every temperature all the wavelengths that came in. And then, so you can figure out how much is being emitted at every wavelength based on your temperature. Things like we're all in the mostly UV or visible or infrared. Infrared, that's why we can see each other with like night vision goggles when there's no visible spectrum. It's catching the infrared. And so we know it's all those wavelengths kind of in that region of the spectrum because of what Planck figured out. And he probably won the Nobel Prize for it. I can't say that for sure, but I think he probably did. But so yes, you would have to create a big array of all those at a given temperature. You don't even have to create an array because we have a function right here. That's what this function is. Quantum mechanics, one of the foundational big things that quantum mechanics taught us is that if I give you a temperature, then I can tell you what the total emission is for a black body. That's what Planck kind of figured out. In fact, you can look at this figure right here, and that's kind of what I was talking about. At certain temperatures, you emit wavelengths in this region. Different temperatures, you start emitting wavelengths in different regions. And then you integrate over all those wavelengths to get at a certain temperature what is your energy, and it comes out to be this sigma t to the fourth. That's where that came from. Stefan Planck figured out the distribution, this kind of thing, and then Stefan Boltzmann did the integral and figured out this sort of thing. So let's talk about black bodies for a second, if there's no other questions about that. I'm going to erase some of this. I need to change colors so that we can see what I'm drawing. So what is a black body? That is one of the big things that quantum mechanics, modern quantum mechanics has told us, is it figured out that if we can talk about this hypothetical thing called a black body, which we can make pretty close to, we can approximate pretty close to a black body in certain cases, that it will absorb everything that comes into it. And it will also, so it won't transmit anything, it won't absorb anything, or it won't transmit anything and it won't reflect anything, it only absorbs. And it absorbs everything regardless of lambda. So it's not dependent on lambda, it's not dependent on wavelength. It doesn't mean that everything's necessarily emitted, but it means it absorbs everything. And a black body means that at a temperature, pick a temperature above 0 Kelvin, nothing can emit more than a black body at that temperature. And what that allows us to do later is define something called epsilon, the emissivity, which is the fraction of the emission compared to a black body. The other thing about a black body is it's a diffuse emitter. What do we mean by diffuse? It means direction doesn't matter. So I went through in this section and said, all this is complex because it's direction dependent and it's lambda dependent. Well, for a black body, it's not. It's not lambda dependent, and it is not angle or area dependent. And the nice part about that is it allows us to actually do integrals across the distribution. So Planck came in, did one of these foundational results of quantum theory, and found out that the wavelengths for a black body at a certain temperature is described by this quantum mechanics type looking equation. And I know you all love those quantum mechanics types looking equation, but you know it's quantum mechanics because it's got H's in there, right? It's got this Planck's constant. So this is for a given lambda. It tells us all the lambdas for a black body at a given temperature. If I integrate over all the lambdas from 0 to infinity, so all possible ones, the nice thing about this Planck's distribution is that you can integrate it. There's a closed form solution. You get this dependence where sigma is this value right here. So if you ever wondered what sigma was, that's what it was. I don't know if you proved that in your Chem 461, is that what it's called? Or Chem 467. So again, Planck figured out this sort of thing, that at certain temperatures, you get a distribution of wavelengths emitted. If I integrate over all those wavelengths at a certain temperature, it comes out to be this sort of thing, a constant times t to the 4th. That's the total energy that's coming out of a black body at a certain temperature. So questions about this?
Yeah. So if I had a black body and I shined like a purple laser at it and I shined a red laser at it, shouldn't the purple one absorb more energy?
A black body will absorb all of them totally.
Yeah.
And so it'd be absorbing all of the
what
purples.
light is being applied to it?
Yeah, it would, so like purple might be at this one wavelength. I don't know what the wavelength is of purple, but 530 nanometers or something like that.
Yeah.
It will absorb all that energy.
Other than that.
And then it will also at the same time absorb all the red light you're shining on it. But you're right that the purple light will have more energy in it than the red light, likely, if you're giving it the same generation of power, I guess. Because I can always increase the intensity, right?
All wavelengths of light are being shined at the exact same amplitude.
Is it the same amplitude? It probably is the same amplitude. Yeah, if they're the same amplitude, then the purple one should have more energy than the red one.
Yeah. So this is just for every black body, if the light being shined at it was totally equally uniform between all wavelengths of light.
It doesn't necessarily mean everything's equal. It just means it absorbs everything that gets hit on it. I could have something like a very bright purple laser and a very not bright purple laser or a dim laser and then a red laser. I could shine them all at the same time, and it's going to absorb all those radiations at the same time and reflect nothing and transmit nothing. Does that answer your question?
Kind of. I'm just like, if I had like a black body in a very dark room and the only thing that I shined on it was one red laser and there was nothing else, and then I took the exact same one and shined a purple laser and nothing else, you would think the energy for the purple laser version would be more than the red laser version.
The energy, yes, it will have more energy in it. Yes, that's true. is your question, so what's your question?
So like, I feel like this EB equation should be dependent on lambda still, because we don't know what kind of light is being hit.
Well, that comes into, so this hasn't necessarily told us what is the light is doing to the temperature yet. Because if I'm shining a red light on a object, say a black body, it's going to start heating up.
Yeah.
Right?
Yeah.
But what we're saying is that the emission of that black body will be this much energy out, because it doesn't have to give off everything that it takes in.
So this isn't what's being absorbed, it's what's being put out.
Yes, this is what's being put out. Nothing can emit more than what is put out. Remember, when we talk about absorption, we talk about G's. So we already know that it absorbs everything. Whatever G is, it's going to absorb it. And maybe that's the confusion, is the G can be different, right? I could have a G from the purple laser, and then I can have a G from the red laser, and they're all hitting the same object. It's going to absorb all of those, and it's going to start changing the temperature of that black body. It will not necessarily emit red or purple light. It will emit whatever temperature it's at because of that light. Does that make sense?
Yeah.
Okay.
Well, thanks.
Other questions before we go on? Okay, so this is going to be a foundational thing that we're going to build on, this limiting case of a black body. And then for real objects, we're going to define properties, the emissivity, that tells us the fraction of that type of material that is actually being emitted. That epsilon, you can look in table, let's see, table 12.3. That doesn't look like a really great 2, but it's 12.3. It gives epsilons for a lot of different surfaces. Now, in general, shiny surfaces have very low emissivities. They don't, that's because mostly they reflect things and they're not giving off a lot of things. Dull, dark objects have very high emissivities, but it's not always clear. So you just kind of have to look it up. Like white paint on a metal surface actually has a pretty high emissivity, and so does black paint. I think it says in that table. I don't want to bring it up right now because it'll take forever. But so you just have to look them up. That's kind of the basic thing. You look up emissivities. But shiny surfaces usually have lower emissivities than dull surfaces. Dark objects usually have higher emissivities than white objects. That's why we like white cars in Arizona, right? Because they reflect a lot and they are, well, I guess it doesn't have, we like them because they reflect a lot. But dull surfaces give off things closer to black bodies. So what are some simplifications that we can do? Well, let's first talk about emissivity. Emissivity is not equal to 1 unless it's a black body. It's always less than 1. The other thing is that alpha, do you remember what alpha was? Alpha is the amount that's absorbed. A black body absorbs everything. A real body will not necessarily absorb everything. Some of it's going to be reflected, some of it's going to be transmission. So for real objects, epsilon's not equal to 1, alpha's not equal to 1, and epsilon and alpha are not necessarily equal to each other. The reason I put that in is because Kirchhoff's law, which we'll talk about in a second, assumes that, and it's usually a bad assumption. Now, also note that, again, epsilon and alpha are dependent on lambda in general, right? My bones absorb a wavelength of light like X-ray, but my tissues do not. It's dependent on lambda. And so when you go to a table, you may, if you're really trying to do this well, you may need to see what the lambda dependence is. Now, we don't know the lambda dependence for a lot of objects. We usually only know it for the things that might be needed in space or that might be in a process that goes by radiation, that is driven by heat transfer driven by radiation rather than by convection. And so usually you don't have that lambda dependence, but if you do, you would use it. So kind of the take-home message again with this is table 12.3 has values for alphas and epsilons. And we'll see in a minute why we need that when we start doing some energy balances. But just kind of know that you look those up, and table 12.3 is what it is in our book. Kirchhoff, to make his life easy, said, let's just assume epsilon is equal to alpha. And this is where you get this Q radiation that we got at the beginning of class that says it's going to be epsilon sigma T surface to the fourth minus T infinity to the fourth. So Kirchhoff came along and said, if the epsilons and alphas are similar, we can write something like this. And we'll see in a minute why you can write that. So when is that valid? It's valid for small objects in very large places. So if you had a very small object like the sun, like the earth compared to the sun is humongous compared to the earth. And that's one of the reasons the sun emits like a black body, at least to us on earth. And then the other thing is the object and the enclosure are at the same temperature. And so it's not a really great, because sometimes that's not true. It's really not a great assumption. A gray body is a better assumption that is good for most engineering calculations. It assumes alpha is not equal to epsilon. So you have to look those up and say table 12.3. But it does assume that alpha is not a function of lambda and that epsilon is not a function of lambda. That's why there's only one value for every lambda and sigma in epsilon. A diffuse gray body, this is kind of a term we use to say there's no angle dependence. Okay, and we're almost always going to do that. The way you know if you can't do that is, well, you're always going to do it in this class because we don't have data for it otherwise. But this goes to the fact that if you had a table that gave alpha values as a function of, say, lambda and direction, theta, then you could do your own integrals. We're not going to do that. And so the kind of the bottom line is the gray surface is what we're going to usually do in calculations. So what does that mean? That means I have to look up alpha. I'll put look up alpha, look up epsilon. These are different numbers, and that they're not angle dependent. And that's going to simplify our life a lot. Now that none of this stuff will make sense maybe until we do an example here in a little while. So if it's not quite sinking in, it's okay. We're going to return to it. We got to get through a lot of definitions first. Let's talk about big irradiators. So remember, what we're trying to find usually is we have some sort of object and it's got some radiation that's coming in. And then you might need to do an energy balance here because you might have emission coming out and you might also have Q convection. And we've been doing convection all year, right? That's HA T surface minus T infinity. If we assumed Kirchhoff's law, we would say Q is something like Q radiation is epsilon sigma T surface to the fourth minus T infinity to the fourth. And we could figure out then this total energy balance. And you've actually done homeworks where you did this. But usually we're going to assume a gray body. So what do we do to figure out how we describe this incoming radiation? If what's ever producing this irradiation is very big and very hot, like the sun, or very cold, maybe like the atmosphere, we can figure out what this G is by assuming the object that's generating it is a black body. And so what does that mean? That means, to a very good approximation, the sun acts like a black body where its temperature is 5,800 Kelvin. So I have the sun here. It's going to emit down here to me. And I want to know how hot I'm going to be on a hot day or whatever. This irradiation that we gave the letter G, I'll be able to get from sigma times 5,800 to the fourth. Does that make sense? So that the sun is acting like a black body. Now I'm going to give you a little caveat to this. I'm going to say that I am on the surface of the moon first. Why is that? Let's say that I'm on the surface of the moon, and you know, the man in the moon or whatever. It's going to be that. When I'm on Earth, because air molecules scatter light, the things like ozone keep back irradiation, and also things like CO2 or H2O, those greenhouse gases, they also screen out IR that's coming from the sun. So in general, once I get down to the Earth's surface, then the sun can be less, it's going to be 950 watts per meter squared or less. If it's a cloudy day, you're going to have less sun. If it's a bright sunny day, you're going to have, you know, close to like 950 watts per meter squared of irradiation from the sun. So that's kind of where those numbers come from. Usually what you're going to do when you do a calculation is say, I want to know how hot a tank of gasoline is going to get on a hot summer day, because I want to make sure it's not going to get above its auto ignition temperature. I want to make sure, right? That's a big deal if you're in the oil industry. You don't want to blow something up. I have to take into account all that sun irradiation, and I might want to do it on the brightest, hottest day I care about. Okay, so questions about how we deal with solar irradiation. It's basically going to be a number 950 or less if we're on the Earth's surface. If you're out in space, it's going to be the highest value, something like this. If you're in the outer atmosphere, something close to this. Any questions on that?
So that's just the number that will be given, the G value?
Yeah, it'll usually be given. Or if I was doing some sort of design calculate, for this class, it'll be given. Or just go to your notes and use this value. If it's a design calculation, right, in your real life, when you get out, it's going to be this value or something less if you're designing something for on Earth. If you're working for NASA, then you're going to use higher values. Either you're going to be in space or satellites in the outer atmosphere, or I guess they're way in space, but or planes or weather balloons that are high in the atmosphere, it might be higher. Does that make sense?
Yep.
Now, whenever you deal with solar irradiation, remember what we're going to want to do is we're trying to do this energy balance on whatever's hitting G sun. So this is G from the sun. It's usually going to be a number, say 950 watts per meter squared. And then I need to know how much of that is being absorbed. If it's transmitting through something, it's not going to affect my energy balance. So how much is absorbed? That's where table 3 comes in. I need to know alpha, that's the amount of absorbed, times G sun. That'll tell me how much of that 950 is actually being absorbed into the body, whatever object I care about. So I might have 950 watts per meter squared coming in through my window, but most of that is going through the window and not heating the window up. It's going through and heating up the carpet or the other part or the air in my house or whatever. And so things that have a high transmittance will have a very low alpha, and so you won't get a lot of that 950 watts per meter squared heating up the object. If I have a black car in Arizona, all 950 watts per meter squared is hitting that black car and heating up it and everything else inside, so to speak. Does that make sense? Now, here's something that you want to remember. You can never use Kirchhoff's law with solar irradiation. And the reason is because the wavelengths that's coming in from the sun, they are at a much different part of the spectrum than the wavelengths that things on Earth will be giving off, like me or you or objects out in the atmosphere. That means, if you kind of go back up to this, the sun might be here in lambda, and we might be, you know, way over here in lambda. And so the absorptivity and the emissivity in that case are almost never the same. And so what you're going to do is look up table 12.3, and you're going to get the alpha value And then when I'm doing my energy balance and I need to know how much emission I have, I'm going to have to get the epsilon value. And they're going to be different. So table 12.3 has 2 columns, one for alpha, one for epsilon. And that's kind of what I explain right here. Because the sun, the solar irradiation from the sun is in such a different region of the spectrum than things that we emit. We're usually in the infrared or near UV. The sun is usually in the high UV, right? High energy and high visible spectrum. And so alpha and epsilon are almost never the same, so you should not use Kirchhoff's law. Okay, that's how we deal with the sun. It's usually just going to be a number coming in, and then I got to get an absorbance. Second thing is the sky. The sky acts like a very big thing. It's composed of a lot of gas molecules, and it does a lot of stuff to the sun, to the radiation that's coming in, but it is at a finite temperature. All those gas molecules, if you think about them as one body, are at a finite temperature. And the atmosphere that might be, you know, down here on Earth, and we're down here, the atmosphere acts like a very big body. And on a clear night, the temperature of that will be about 230 Kelvin. And on a cloudy, warm day, it might be 285 Kelvin. What does that mean for us? Again, what I'm trying to do is figure out how much G is coming into me from the atmosphere. And it's going to act like a black body at one of these temperatures. And so if it was a cloudy day, I would say that G is a sigma times, or if it's a clear night, sorry, clear night, 230 Kelvin to the 4th. That's how I could figure out how much the atmosphere is sending down to me on Earth. If it's a warm, cloudy day, then I would put 285 Kelvin to the 4th. Again, and that's kind of what I say right here. What we're trying to do now is, because the sun and the atmosphere are big things in engineering. Anything you're out, anytime you're outside, you've got to kind of deal with radiation from those two objects. How do we deal with that? The sun acts like a black body, but then it gets scattered as it goes through the atmosphere. And so what usually gets down to Earth is basically a number, 950 watts per meter squared Kelvin on a clearer day, down to almost nothing on a very, you know, cloudy night. Well, maybe not nothing, but because we still have light, but on a cloudy day, it's going to be much less than that. The sky is a very big object. It acts like a black body at fairly cold temperatures. And so I can figure out how much G is coming into me from that black body. And I'm going to need to add up all these G's coming into me from the sky, from the atmosphere, things like that, to when I do my energy balance to figure out what the temperature is of this object. Okay. Any questions on that? We are doing good on time because we just kind of want to get through this number 7, and we're going to do a lot of examples next time. So all I do here in number 7 is kind of summarize how we describe this kind of energy balance for radiation coming into an object. And so I will have a G coming in, and then I will have an emission going out. Now that I might have multiple G's, but I'm just going to restrict it to 1 G coming in, 1 G coming out. In general, the net radiative flux, so this is just radiation. We're neglecting conduction and convection here just to be able to write the energy balance. So we're just talking about radiation here. The stuff coming in is what fraction I absorb of the irradiation. And it can be lambda and theta dependent. The stuff coming out of me, because I am at something higher than 0 Kelvin, is what I'm emitting. It's a fraction of the black body. This is black body. And this is my emissivity, epsilon. It's already there. And it can be a function of lambda and theta. So that's kind of the most general thing I can write. Functions of lambda and theta, and then relative to black body and relative to how much is coming in, G. If I consider myself a gray body, which is the best engineering assumption, Ooh, I better not do that. Let's do that. Then that basically says it's not a function of lambda anymore. The epsilons and alphas. So remember, G is just a number. It's coming in, say, from the sun, 950 watts per meter squared. It's coming in from the atmosphere. It's something like that. And what fraction of that am I doing? So gray body says it's not a function of lambda. I almost always assume gray body. Diffuse gray body means it's also not a function of theta anymore. So maybe I should write it like that. I missed an epsilon. There should be an epsilon right here. Sorry about that. Everyone see that? I'll put it in purple. So there's an epsilon that should be right here. Draw that in. And this is actually most common. And it's pretty good. Maybe I should have written this object down here, because I would argue that's probably the best engineering assumption unless you're working for NASA. Kirchhoff's law is the bad assumption in most cases, especially if it's involving the sun. If you're involving an oven, like a small object in a big oven or something like that, then you can often use Kirchhoff's law. That's where we say alpha is equal to epsilon, and you can pull that epsilon out and you get this kind of thing. And so this is still just a number, but then if we put something in like we assume it's a black body, then this becomes EB and we get this Kirchhoff's law type thing. We're almost always going to be trying to do this first. And so we need a different alpha that's equal to epsilon. If it is something in a small object in a big place that's not the sun, so small object in big cavity, and the object is not the sun, then we can simplify it to be this. And that is where we're going to stop for the day. So questions kind of before we sign off. Your homework's posted if you want to start it, but remember your homework number 32 is due Friday, so that's the heat exchanger problem. Homework 33 is not due till Monday, and then homework 34 will be due Wednesday, but it's posted if anyone wants to start their radiation type homework. And then we're going to go through some examples next time. And I've intentionally, I don't think I posted the filled examples on Learning Suite because I want to work through them in class to get you to think through them. So we're probably going to break out into groups again. So questions? Okay. I don't know if anyone's in the chat. Nathan asked if the grades are up yet. I've talked to the one TA that's still finishing. He or she was sick, and that's why the grades aren't done yet, but he or she has promised me to be done by tomorrow. And so you should have your test grades on Friday. Any other questions? Okay. We will see you guys on Friday then, and keep going with radiation.
Dr. Knotts, can I ask a question? Not
Yep.
about notes or anything, just personal.
Yeah. Is it personal enough you want to get onto Zoom?
Yeah, it's just about the competence. I sent you an email earlier.
Let's do that. Zach McAllister, it looks like you also want to meet after class. Zach, send me an email and we'll try to meet somewhere around 3:30ish. And then I'll meet with Connor right now. Connor, I'll send you an invite.
All right, perfect.
Okay.
Thanks.
See you, everybody. See you later.